So let me know if you have any question regarding the discussion that we had last class. Okay, so let me briefly recap. The basic logic that we had was, let me write down from scratch. That's always a good idea. So the logic was as follows that
Sir,
yeah.
so the assignment problem, the second one,
Yes.
like, would you be willing to like discuss it to an extent, because I'm facing difficulties in proceeding?
Okay, maybe we can discuss it after the class today.
Sure.
Okay. All right. So let's come to today's lecture. So essentially, we talked about fork space. Essentially, it is a multi-particle space. Instead of multi-mode space, right? Occupation number space. So that's the way we think about it. And the reason for that is simply that we do not want to think of P and P prime different these kind of modes as separate. Or so if you have one occupation number here versus 0 versus occupation number here, so these two are related by some symmetry transformation, by boost, for example, or rotation. So so we do not want to call them different things, because it's just like a train moving is still a train. You don't call it a different name. So this is the reason why we wanted to say it's better to start from a quantum case in a multi-particle space. And then we said that since A dagger P and A dagger P prime should commute, and we saw that it is commute or anti-commute, right? So we naturally lead to identical particles. But the point is that it's an identical actually more than identical particles. I will say it leads to racial equality, because independently, whatever two bosons we have, we always get, it doesn't depend on the species also, depending on two bosons, A dagger P and A dagger P prime. So let me call it in a more general way, A dagger P sigma n and A dagger P prime sigma prime n prime. So commute if if both are bosonic, or maybe just to say if one of them are bosonic, if one of them is bosonic and anti-commute otherwise, right? So this is an ultimate racial equality, because the particle species doesn't matter. It will always commute or anti-commute. So that's a very natural thing to do from the point of view of modes. But this is simply also a matter of convenience. If you look from the particle point of view, I mean, you could have written, for example, there's one way to write this. If you do not think of racial equality, you try to order them somehow. So you write the electrons first, and say then you write photons, and then you write quarks. You try to give them some order, right? And that's it. So and then you keep this order forever. But there is a problem with such an ordering. The problem is that suppose you have somewhere neutrinos along the line. Suppose the electrons are neutrinos. Then you will see that electrons and neutrinos can be rotated to each other by some gauge transformation. The SU2 gauge transformation in a way. Anyway, there is some transformations that can actually rotate these things. Or there can be either gauge transformation, or there could be even symmetry, other kinds of global symmetry transformation. We'll see the difference. Anyway, there are some symmetry transformations which can interchange particles. And then, of course, it doesn't make sense to think of them in this way. And if you put in enough kind of symmetry called supersymmetry, then actually you can even transform a boson to a fermion and a fermion to a boson by the supersymmetric transformations. So for example, if you have sufficient amount of supersymmetry, all particles in a given theory are simply related to each other by some symmetry transformations, if you have sufficient amount of supersymmetries. So in that sense, it's very natural to think of, in principle, that everything could be related to each other by some transformation. Or you could think of some highly unified perspective, like all of the particles come from the vibration of something like a string, and therefore there is no reason to distinguish. Also, all of them are made of the same stuff in a way. So you need not distinguish them, for example. So this keeps the so this point of view is rather is not a very good idea to order particles this way. But even if there is no symmetry whatsoever, you could simply say that this permutation symmetry or this ratio equality is simply a matter of choice or a matter of convenience. That's all. I mean, there is no fundamentally nothing is going to get wrong, because anyway this commutation relation holds. And if you write your things in a symmetric way, if your wave function is symmetric, symmetric wave functions are convenient. That's all. But the fundamental thing, of course, is that these are commute, or if one of them is bosonic, A daggers will commute if one of them is bosonic, and or they will anti-commute if both are fermionic. So this is something always a true statement. This is a very fundamentally true statement. But the wave function on its own, the symmetry or anti-symmetry of it is sort of a matter of convenience. That's all. I mean, one could have done it otherwise, or could have just chosen a member. But in any case, then you have to put in some equality that these two wave functions are equal. But this makes life very inconvenient. It's very convenient to think of the wave function in this way. It's symmetric. And then we said that, and then we said that there is this the Folk space has this fundamental assumption, as I said. They are all states are created by acting A dagger P sigma n on the vacuum, right? This is what we assumed. So you see that this is the only assumption, or okay, there's also another small assumption, the norm assumption, but it's not really an assumption. But this is basically it's the only fundamental assumption that we are putting in, that all states are created by the action of this creation operators on the vacuum. So if you remember, what we did was, in the case of the harmonic oscillator, we started from a Hamiltonian like this, right? And yeah, p squared by 2. Okay, allow me to just put, okay, if you would, let me put omega naught square and m, let me omit m for the moment. So it's a Hamiltonian was like that. And from there, we said that we were able to write this as A dagger A plus Hermitian conjugate. And then, yeah, sorry, not the, okay, we simply wrote it as A dagger A plus half, right? And h bar omega naught. That was how we wrote the Hamiltonian. And then we showed that all the states are essentially created by A dagger, acting A dagger on 0. So we showed that if H is the harmonic oscillator Hamiltonian, h bar omega naught A dagger A plus half, then energy eigenstates are essentially A dagger to the power n acting on the vacuum, or sorry, or on the ground state, right? So this is how we showed, yeah, proportional to n. There was some normalization factor. So this is what we showed, right? But we are not going to do that. So here we are not starting from any Hamiltonian. We simply say that instead of starting from a Hamiltonian, we directly say that that the states are created by the action of A dagger P sigma n on vacuum. Okay. So that's a different starting point. We don't start from an assumption of any Hamiltonian. Okay. So this P sigma n, as I said, the quantum numbers are simply abstracted as Q. So then so by this assumption, then if you act all this A dagger Q1, A dagger Qn on the vacuum, you will get some state which is Q1 Qn, right? So that's all without, and that's the normalization and without any extra normalization. So this is sort of the fundamental assumption of fork space. All right. Then what we showed that, then what we said, let us just define a norm, which is as follows. So we have, say, Q1 prime, Qm prime, and Q1 Qn, right? The norm has to be symmetric. And the simplest thing that one can do is to say that this is delta Nm and sum over permutations and delta P, where delta P is simply the sign of the permutation, which is plus or minus 1, depending on how many, depending on plus if depending on even or odd number of fermionic exchanges. And then we have pi I is equal to 1 to n delta Q1 prime minus Q, sorry, Qi and Qpi. So this is simply, this is the norm of this is the norm, right? Okay. So once we define a norm, we can define a Hermitian conjugate, right? So a Hermitian conjugate is always defined with respect to a norm. Okay, right? And so this norm implies that the Hermitian conjugate of A dagger will have the following action. If you take A of Q and act it on a state Q1 Qn, right? So suppose, so we made a simplifying statement that that we suppose that all of them are fermionic or bosonic, all fermionic or bosonic. But obviously, you can generalize. If I give it to you to think. So first of all, you have to take. So this will be sum R is equal to 1 to n plus minus R minus 1, right? Yeah, R minus 1. And then we had delta Q minus QR, and then Q1, QR minus 1, QR, and Qn, right? And where the plus is for bosons and minus is for fermions. But if you have both bosons and fermions, you have to bring the Rth particle, Rth thing to the front, and you have to just simply say how many of these are bosons and how many of these are fermions. You have to simply count, and based on that, you'll get the sign. Okay, but that doesn't change anything. Okay, so this is something we proved yesterday. Okay, remember? And then we also showed that we get a dagger Q, AQ, sorry, A. And then we showed that it implies that A of Q, comma, A dagger Q prime would be delta Q minus Q prime if one is bosonic and is equal to, and otherwise you have AQ, A dagger Q prime equals to delta Q minus Q prime if both are fermionic. Right? This is something that we also showed last time. So I hope you understood the points. So the basic logic is as follows: that in the fork space, you already assume that there is an existence of an A dagger operator that generates the multiparticle states. Okay, so that's the main departure from the usual thing. Okay, but this is basically very semantic. I mean, the good thing is that we haven't commuted to any Hamiltonian, right? So the point is that, and then what you simply say that, yeah. So the simplest Hamiltonian that we can get, of course, is okay. Let's first do one thing. So first, let us make a statement that any operator in fork space can be written as, so let this operator be O, and we can always write such an operator in this form. It is sum n is equal to 1 to infinity, sum m is equal to 1 to infinity, dq1 prime, dqn prime, and dq1, dqm, and a dagger q1 prime. Yeah, a dagger q1 prime, a dagger qn prime, and then aq, aq1 to aqm, and then we should have some c nm, q1 prime, qn prime, and q1 qm. So this is how we can always write down any operator, where as you see that this is simply a number, whereas these are operators. So you can always, so this is always called a normal ordered form. So in the normal order form, you're always writing all the a daggers to the left and all the a's to the right, right? So all a daggers to left and a's to right. So for example, of course, if we take a vacuum expectation value of this object, so what is going to contribute when there is no a daggers and no a's, right? That's the only thing that is going to contribute. So this is going to be C00. That's all. And the C00 is the first thing. Maybe in that case, I should write n is equal to 0 to infinity, n is equal to 0 to infinity. Sorry, not 1. Or maybe what I should do, I should write n is equal to 1 to infinity, m is equal to 1 to infinity, and plus C00. I should just put it by hand. And but there would be possibilities that you have all a daggers and not all a's, right? So yeah, so in that case, yeah, okay, I have to do it a little bit more carefully. So let me see, the best way to write it would be probably for n is equal to 0 to infinity and m is equal to 0 to infinity already. So then I don't need to do this. But anyway, so that's it's understood that if m is equal to 0, then there is no integrations involved at all. Okay, so now of course, if O is Hermitian, right? If O is Hermitian, then you should have some relations. For example, if O is Hermitian, then the term proportional to say a dagger q1, a dagger q2, and the term proportional to just aq1, sorry, yeah, aq2, aq1, say, if you allow me to write this way, because I can always, I mean, of course, integrating over these q's, so it doesn't matter. So these terms has to be complex conjugates of each other, right? Because this is a Hermitian conjugate of that. So if there is if O is Hermitian, then there has to be relations between these coefficients C and M's. So for example, C20 and C02 will be related by complex conjugation and transpose. So basically transpose, because Q2 and Q1 have interchanged. So basically you should have CT0 is equal to C02 dagger, right? So you will get these kind of relations if your O is Hermitian. So if O is unitary, then you will get some other kind of relations. But it doesn't matter. It doesn't matter whether O is Hermitian, unitary, or whatever. Any operator can be written in this way. Okay. Yeah. So now it is easy to see why. It's very easy to see, and this is the same thing that I think we have already discussed. So this is easy to prove, because suppose I take, because my assumption is that these are the Hilbert space. The full Hilbert space is generated by these A daggers acting on the vacuum. So therefore, if I take some matrix element, right? So how should I take it? Yeah. So let me take Q1, say Q1 prime, Qn prime O, and Q1 Qm, right? Let me take some matrix element like that of these of this thing. Then using very similar techniques that you have already done before, you can easily see that you should be able to write this operator. So we did it in the case of quantum mechanics, remember? So you get that this matrix element has to be C. Maybe I should call it a different name. Let me call it L. Let me call it K, so that it's not getting confused. So this is CLK, right? Times factorial L factorial K. This should be giving me this, plus terms with L equals to, sorry, plus terms with M is equal to L and N less than sorry, M, I have to write this way, I think. Terms with M less, sorry, N less than L and M less than equal to K, or N less than equal to L and M less than K, right? This is what I will get. Now this factorial L factorial K simply comes from the fact that, so that's easy to verify. You can verify this. So why there is this factorial L factorial K? Simply, it's simply a reflection of the fact that you have, yeah, this is how we wrote it. And now if we have AQ1s acting on, so first we have a product of AQs acting on this Q1, Qm, right? And so each of these A's would give you one factor, and then yeah, so yeah, you can check actually if you want. So the first A would give you one factor, and then the second A would give you factors. It will keep yeah. You will get a factorial M factorial M factor from here actually, and similarly you will get a factorial K factor from here. Okay, just work it out on your own. I leave it a small exercise for you. Okay. So now what you get from here, so we can always choose CLK such that to reproduce the matrix element on the left hand side. Okay, so whatever the matrix element is on the left hand side, one can always choose CLK as a reproduce, because here the terms which I don't show are simply has N less than L or M less than K. So there are always terms which are lesser, and these are, say, already known to me. And suppose suppose these are, so I can so this is something that you can use a recursive argument. So suppose you say that you have determined all of these terms with N less than L and M less than K, and so then if these are already known to you, and you want to, and you decide a matrix element for this operator between these two things, then you can always choose a CLK such that you can reproduce that matrix element, right? So that's argument, and this is something that you can recursively argue. So therefore, we should be always able to do this, right? We should always be able to choose a CLK to reproduce the matrix element of any operator. Okay, that is argument. Okay, so that's more or less it. And then we sort of say that, okay, to have dynamics, right, we need to choose a Hamiltonian. Now, what is this Hamiltonian we will choose? We simply choose the simplest choice is of course, it should be a number, but a number, we can always choose the ground state to have zero energy. And so what we can do is simply have the simplest Hamiltonian would be then dq, if you wish, a dagger q, aq. Okay, let me just say one thing. A simplest Hamiltonian, which is also a choose the simplest local Hamiltonian. If you need a local Hamiltonian, we should have like this: H is equal to dq times the first simple thing should be a dagger q, aq. In general, it could have been q1, q2, but if you want locality of the Hamiltonian, you have to do this. Okay, so that's because, of course, if you want to go back to real space, right? So you have to do the Fourier transform of the Hamiltonian as the, so you can do a Fourier transform, and okay, I'm going to show that to you. Okay, just hold on. So this is the, so for a local Hamiltonian, you should have the same Q's, and then there is some epsilon of Q, which would be the one particle energy, plus there is also a possibility of this kind. You cannot rule out. This is a dagger Q and a dagger minus Q. Let me put it this way, it's Cy, and delta Q plus, and because the Hamiltonian is okay, maybe if you wish, I write it this way. I've done this way. Okay, so that's the most general local Hamiltonian, right? But you could always see that you could redefine, and this is something that that I'll leave as an exercise to you. This will be one of the exercises in the upcoming assignment. Is that you can always diagonalize this Hamiltonian to some B of Q, which has which is a dagger Q, say alpha a dagger Q plus beta a minus Q, and B dagger Q would then be equal to alpha star AQ plus beta star A dagger minus Q, right? So yeah. Yes. So you can always do this, and you can always do this transformation such that you can also such that you have the same algebra, that is BQ B dagger Q or is equal to BQ B dagger Q is delta Q minus Q prime, or if for the case of fermions, you have BQ B dagger Q is equal to delta Q minus Q prime. So either you have the commutation, and BQ and B dagger Q, of course, will commute. So you have BQs and BQs. The commutation anti-commutation of BQs would simply be and if you wish, B dagger Q equals 0, or B dagger Q equals 0. Okay, so this is essentially, I will give a very detailed assignment. So because we're running short of time, usually I even work this out in the class, but this little bit shortage of time, so I will slightly hurry up. And have you seen such a Hamiltonian before? I think you may have seen it before in some other course. Have you seen this before? Have you done, if you have seen BCS superconductivity, you may have seen such an Hamiltonian. So in that case, for the BCS theory, you get such terms in the Hamiltonian. Now the origin of such terms comes from the fact that, so you have a condensate of, okay, so you have terms of your Hamiltonian of this kind. Hamiltonian has some fourth order term, some dq, so dq1, dq2, if you wish. And let me write it this way: a dagger q1, a dagger q2, and a q1, a q2. So you have terms in your BCS Hamiltonian. So these are essentially four particle interactions that you get. So one way to think about such interactions is as follows: you have some Fermi surface, you have a pair of particle and hole here, and then you can scatter them to another pair of particle and hole on the Fermi surface. So these are some interactions on the Fermi surface. And then I will give you an exercise to work it out on to work out the details. So I'm just sketching it for you. So you have something of this sort, and then what you say is that you have some kind of condensate, which tells you that the vacuum expectation value of AQ1 and A minus Q1. So Q here also stands for spins and the momentum. So there is it's P half and minus P minus half, and hence is not equal to 0. So the vacuum expectation value of this is not 0. And if you say that, so say you have some, so basically you do some kind of a mean field and you replace this term with the vacuum expectation value. This is what you call the condensate delta. So you call it delta Q. So you get a term in your Hamiltonian which looks like this, which is a dagger Q, a dagger minus Q, delta Q. And this is sort of an ansatz that you put in, that you say that it is possible. The reason, so the rough argument. Okay, so then I have to go to BCS theory about why such a thing can happen. So basically the idea is as follows: that if such a vacuum condensate exists, so note that the net momentum is 0. So essentially what you have from here pictorially, that you have some lattice, and so the electrons will repulse each other, but then there are also phonons. So suppose one electron goes past and it creates some kind of lattice distortions. It moves the lattice along, and then the other electron which follows it, then these other electron that follows it will see some net positive force, and it will be attracted towards it. So essentially, if the lattice mediated interactions can be attractive, and therefore you might expect that these electrons can form some pairs which are called Cooper pairs. So they're kind of correlated, and then you get some vacuum expectation values. So in the vacuum, there you can form these correlated pairs, and expectation values of these are non-zero. And this is happening because of this, because of the lattice mediation. But however, you could simply think that all that is need to assume is that in effective approach, you do not care whether it comes from the lattice or not. You simply put a U naught, such that U naught is less than 0. In some range of mod P minus P prime, if you wish. So the main idea is as follows: that so this will only happen if the electrons are very slowly moving, have less energy, because if they move fast, if this electron moves fast, then it will not see the lattice distortion, because once this electron moves, it takes some time for this lattice to be distorted, and that depends on there's a virtual phonon, and you have to look at the pole energy pole of that. So there will be some delta or something of that kind, where okay, there is some other notation for that. But anyway, so there is some time scale which takes time for the lattice to get distorted, and the electron has to move slowly compared to that. So as long as these electrons are slowly moving or less energy, so they should be on the Fermi surface. So that's when they have the minimum possible energy, and therefore they can get correlated. So in some range of this U0, it has to be attractive. That is what we captured here. So if it is so, yeah.
So could you explain that circle again? I'm sorry, a little late, so I couldn't catch that.
Circle. Sorry, which circle? This one?
Yeah.
It is simply the Fermi surface, and the lowest energy, if you excite the system, the lowest thing, so all the states are filled. The lowest energy will be one of electron kicked out from here, and then there will be a hole. So particle hole excitations are the thing. So actually what I should, I should have written it in a better way, this Hamiltonian. But anyway, so the point that I'm trying to explain is that how do you get such terms in the Hamiltonian? That simply comes from the expectation that you will have, that there will be non-zero vacuum expectation value of these two electrons, which have opposite momentum. So there's no momentum, no net spin, but they are correlated. And that happens if they are on the Fermi surface, if both the electrons are on the Fermi surface. So, and the correlations come because of this vacuum medium. But in the mean field approach, you don't have to put it, it just simply comes out directly from the field theory, because you can, so suppose you have some leading term like that and some term like that, and this delta Q, and this is something known to you, you can compute the energy and minimize it. And you see that and this is sort of the mean field that we solve for, this is a condensate. You see that there is a particular value of the condensate which minimizes the total energy. And that is how you can compute the condensate, actually. And this is something I'll give you an exercise so you can do it. It's basically BCS theory put in the language of many body, or in the folk language, right? So, but here in this language, you do not need to, you just need to have some intuition that where this such a thing can come from, and then you put it in this effective field theory language. You don't have to, you have simply put in by hand. But obviously you can do better. What you can do, you can write down a theory of electrons and phonons as a complete many body systems. And then you can show from complete rigorous field theory that such a thing is possible. And for that, you have to wait till the end of the course. You have to look for how to solve for the Green's function. So you have to solve. So basically, you see that such condensate can come from the systematic computation of the Green's function. So you have to give me equations for Green's functions. So what you do is that, for example, so remember that we had this effective action which gave me the expectation value of x of t, how it evolved in time. You can similarly write this in field theory, this becomes gamma of phi. It tells you how phi of t will evolve in time. But here what you need is expectation value of the Green's function, how that will evolve in time. So that gives you an effective an action for how the, and this is what I call Schwinger-Dyson equations. So if you want to have a very rigorous approach where you do not put anything by hand, you have to study the Green's functions, how they evolve, and then you have to study the electrons and the phonons together. And there's a beautiful theory called the Eliashberg theory, which does that using the Schwinger-Dyson equations. And then using that, you can actually compute it from first principles, what is this condensate. So you don't have to put anything by hand. Of course, the only thing that you sort of put by hand are some lattice parameters. Like you ask your friend who does some numerical computations to give the band, solve the band energies or whatever. And that's the only input that your friend gives you. And other than that, you can compute everything from first principles. And this is called the Migdal-Eliashberg approach. But this is something very advanced. But you already see that what I wanted to say, basically, that any many body system can be understood in the language of field theory. Okay, that's one very important thing. For the moment, we have not introduced fields. We have only introduced A daggers. So I'm coming to that soon.
Okay, got it.
Okay. All right. Now, what I would do is as follows. That so then, of course, you can have higher order terms which are compatible with locality. Okay. So obviously it looks like A daggers. Then okay. So the main point that I wanted to say is that so as long as the Hamiltonian is local, and if you remember, we said that H goes to H naught plus V, where H naught is essentially particle number conserving, and V is the interacting part. So you get the fundamental thing called S matrix, which we discussed earlier, and then S matrix satisfies the cluster decomposition property. If H is local. So basically what we will show is that it requires that H is constructed out of some fields, which we're going to introduce now. So the basic logic is as follows, is that, so you could say that why we start from fork space, and you can say that, well, the fork space is a natural starting point, is simply that as long as I have this creation annihilation operators, and that's how I can construct my Hilbert space, I simply find that the S matrix, the fundamental observable that I get about how the fundamental, because any process can be, any physical process can be broken down into S matrices. And so then these S matrices satisfy this important cluster decomposition property, which means that if there's a transition here and a transition here, they will factorize if they're far apart. The transitions far apart from each other. So essentially, this is the logic behind quantum field theory, as saying that, okay, so this is something that, this is how it should work out. Okay, so that's sort of the logic. And but in any case, what I wanted to say here, so I will give you an exercise, a bosonic and a fermionic exercise. Is really very simple. You should work it out. It looks complicated, but if the way I will write the assignment, you'll see that this is the simplest assignment in your so far, and you can easily do it in a few days, 3 days, I mean even 2 hours if you wish. So if you will see, if you work out the assignment, you will see that then you could simply write this Hamiltonian after all as B of Q plus B dagger Q. B dagger Q BQ. So you can get rid of this off diagonal terms by some diagonalization, and this is the technique. And this is often known in literature as Bogoliubov transformation. And by the way, some similar transformations also appear in the context of, like, to understand why black holes radiate thermally. So if there's a famous paper of Stephen Hawking where they derive this black hole, that semi-classically a black hole should emit radiation like a black body, also use this kind of transformations. The Bogoliubov transformations, but it had a little bit different origin from what I'm saying. But anyway, so this is more or less the logic why we always start from a Hamiltonian, always of this form, a local Hamiltonian. The simplest local Hamiltonian is this. Simply H is equal to some dq, A dagger Q, AQ, epsilon Q. Okay, so that's the simplest Hamiltonian that you can always have. And yeah. Okay, so now I'm going to field theory, or telling you what is the postulates that we use to construct fields.
Here, what is the approximation we are using to remove the second and third term from the Hamiltonian?
There is no approximation. As I said, that there is no second. You simply have to redefine your BQ, and if you can write this in the form B dagger Q BQ if you do some linear transformations.
Okay.
Where BQ and BQ satisfy exactly the same algebra like AQs.
Okay.
So the creation, yeah.
Right. Yes.
Yeah, but there is, of course, another, I'll give you another exercise to say that, So something that is annihilated by B of Q, right? The vacuum that's annihilated by the V of Q is not the same vacuum as that is annihilated by A of Q, right? So what is, because B of Q is a combination of A and A daggers, right? So if A dagger acts on this vacuum, so B of Q is, so essentially the B of Q is a coherent state. So this vacuum that is annihilated by B is a coherent state of the vacuum that is, yeah. So okay, you will work it out yourself and see. So there is, you can write, there is a particular way to write this 0B in terms of the Fock space. Yeah, it is, it will be something e to the power alpha A dagger, where alpha is a special, sorry, this is not the same alpha. This is basically, okay, let me call it gamma. Gamma will be essentially a ratio of alpha by beta. You can work that out. That acts on the vacuum, 0A, the original vacuum. And so essentially the new vacuum is a coherent state of the old vacuum, right? And this is also what you need, what is necessary, because if it were not a coherent state, then you could not have an expectation value like this, right? To need it, to create an expectation value of this kind, you cannot have the original vacuum, because the original vacuum cannot have expectation value with two A's. It can have one A dagger, one A at least. To have something that has expectation values with two A's, this vacuum then cannot be the original A vacuum. It's a coherent state of the original A vacuum. But the zero vacuum, but the new vacuum is annihilated by the B operator. So one way to think about it is, so in this particular case, what will happen actually, okay, what I did was not correct. Okay, let me write it in a better way. Let me, okay, since this question came about, so what you can show that these vacuums 0B is equal to e to the power, let me write this way, dq, e to the power some gamma. I'll leave it as an exercise. This is an assignment problem to compute gamma. Gamma A dagger Q, A dagger minus Q, right? And acting on the original vacuum 0A with some normalization factor, which is not important. So now if you have fermions, then you see that e to the power gamma, if you expand, you can only have to keep the first and the next term, right? So you get then 1 plus, if you have fermions who have simply pi q, if you wish, you can rewrite it in this way: gamma A dagger Q, A dagger minus Q, 0 Q. So this is exactly the BCS ground state. If you have taken a course in condensed matter physics, this is exactly the BCS ground state, right? You have seen this wave function before. That's how the BCS originally wrote down the wave function. Because if this is fermions, you cannot have twice of this, so you get only, so the expansion simply stops at the quadratic order, because A dagger square is 0. Okay, you have seen this before, so something like this. Yeah, and in this BCS ground state, you find a non-trivial correlation function, right? And so it's a self-consistent argument. It's basically a self-consistent argument to say that such a thing can happen. And again, for such a thing to happen, you need some attractive interaction, and that's the key between this. Yeah. Anyway, so I think yeah, I think you should. So this will be all part of some assignment. Work it out. And I don't want to waste time on it, because essentially, if I spend time on it, then it will cover at least one lecture. Already, it has covered part of this lecture. So I want to a little bit hurry up. So I think you should be able to work it out in assignment. These algebra are really very simple algebra. I mean, this is something that, and I think it's a fun thing, because when you work it out, you will understand it better rather than just simply listening to it. Okay. All right. So now let us come to field theory. Okay. So as I said, is that I'm not going to start from some action, some classical action, and say that I'm quantizing it. All that I'm going to do is to put in locality and causality together. And you see that this is very, very powerful. In fact, plus Lorentz invariance is important, of course, because otherwise the causality is not well defined. But if I put all of these three things together, I automatically get the classical, I get my spin out, I get everything out from it. So I don't have to put in any extra assumption or all classical field theory and all the standard classical field equations, and also this and also spin. And for the massless gauge boson, in fact, gauge invariance is also a consequence of this. So it is not possible to write a local causal Lorentz invariant theory of a massless spin 1 particle if there is no gauge invariance. The gauge invariance has to be there. Anyway, so those are the so today we will start seeing these things in a very simplest. So there is something we put in as a postulate. The first postulate is that all observables can be constructed out of a field phi x. So there's an elementary field out of which we can construct all observables. That's a very radical thing. And yeah, and essentially you can also put an index n here for the particle species if you wish. But for the moment, let us say there is only one particle. And I will soon generalize this to at least a case of one charged particle. So one charged particle, you will see that in order to have a causal theory, you cannot do it with just one charged particle. You also need its antiparticle. So only when particle and antiparticle come in pairs, you can have a causal theory. You can have a local theory without particles, without antiparticles, but you cannot have a causal theory. So causality is always is always given by multi-particle process, where the propagation of a particle and the propagation of an antiparticle exactly cancel out. So causality cannot be in a single particle. If you have only one particle and not two kinds of particles, you cannot have a causal theory. But this is something that we will see soon, in fact, today itself. But for the moment, let us start with only so essentially it will be a chargeless particle. So that's one assumption. So, but this is not. So basically, this is in this particular case, it means it's a Hermitian field. So let's start with the simplest example, and there is no A index because there's only one particle. And then and furthermore, and this is actually the crucial assumption here. So phi of x is equal to. Okay, so let me also say that this x would denote x and t both. Okay, so corresponding to every point in space and time, you have a field. Okay, so it's like an abstract field. So this is exactly what, for example, Faraday and everybody said that like electric and magnetic fields, and this is something, the intuition of Faraday, right? So what you do is that you simply say that everything is built out of fields. Even matter is built out of fields. Okay. This is a very radical thing. Okay. But this is the only way we can have a causal theory. If we just start with usual quantum mechanics, you can easily see, and you can easily see from here actually, that you cannot have a nice local and causal theory at all. So you need to, this is the only way one can have local causal Lorentz invariant formulation, which is quantum. Okay. All right. So furthermore, now this is the simplest assumption. So what we do is to say this is U some Qx A of Q plus V Qx A dagger Q. Now, since we have a, okay, let me make my life easier, because we are also assuming the particle has no spin for the moment, to make our life simpler again. So we simply say that it is 2 pi to the power 3/2. So you can repeat the constructions with spin, but then you have to assume why there should be a spin, right? And that is why there's a spin at all. So I don't want to get into that complication where the spin comes from. So I think this is something we'll do in the next course, not this course. We don't have time. So in that case, okay, let me, sorry, wait, let me put it 2 pi cube. You Px, and x is both x and p, remember, and a p plus v px a dagger, right? So you see that when I write such a thing, this is the simplest possible thing. Obviously, there is nothing wrong in saying that it will have a cube p, a dagger p. It can have nonlinear terms also, right? But this is simplest starting point. This is the simplest theory, or I would say it's the simplest field theory. Okay, the simplest field theory that we can start from. Now, obviously, this implies already we are committing to Hamiltonian. So actually, it is easy to see then what it implies that the Hamiltonian is a quadratic. If you're Hamiltonian of this form, then only you will have this, you will have something like this. Why? Because your phi, suppose that x is equal to 0, suppose that p is equal to 0, the hypothesis is true. Then we also require that at time t, at arbitrary time t, phi xt, you should have e to the power I ht phi x0, and then e to the power minus I ht should also take the same form, right? Should be linear in AP and A dagger p, right? But this is something that we already did for the harmonic oscillator, right? We know that if H, so remember the harmonic oscillator Hamiltonian was A dagger A H bar omega naught, and we computed how A of t. So what you need to, so remember that these are only, so these are the operators, right? A and A daggers are the operators, right? So if I do the following thing, if I just add this e to the power I ht phi x e to the power minus I ht, what I would get is simply this thing. Sorry, x0. So then I simply act here, right? I have to act it, act on these objects, right? AP and A dagger P. So first of all, we know that if this is the Hamiltonian A dagger A, we remember we showed that A of t is equal to e to the power minus I omega naught t A, and A dagger t is equal to e to the power I omega naught t A dagger. This is something that we already seen in the case of quantum mechanics. And here you see it is true because for what you have here is simply infinite number of quantum mechanical harmonic oscillator. For every p mode, you have one harmonic oscillator. That's all you have. So here, of course, I'm putting h bar to 0, sorry, h bar to 1. Or you can think epsilon of p if you wish, it already has h bar omega naught. So epsilon of p is h bar omega p. You can put it all, think also this way. So there is, for every p mode, we have a omega naught. That's all, right? And there is no other change. So so if I do this here, e to the power, so look, so this is not an operator. This is a number. This is a number. So if I do e to the power IHT, so this operation will only affect this A and A daggers, right? It will not affect these coefficients. So then what is going to happen? So then we have dqp by 2 pi cube. And then you have u p x, and then t is equal to 0. And then we have e to the power minus I omega naught t, but e to the power minus I omega naught t will become e to the power minus I omega p t. That's all. And then you have AP plus v p x 0 e to the power I omega p t a dagger p. So from which you can simply say that u p, by comparing these two, you can simply say that u p x t. But you say that here it is it was x, general x and t was included in this x. So from here you can conclude that u p x t has to be equal to u p x t is equal to 0 times e to the power minus I omega p t. And similarly, v p x t has to be equal to v p x 0 e to the power I omega p t. So
what was the hypothesis here?
The hypothesis is that your phi of x is linear in A and A dagger. That's the hypothesis. And this is only possible if your Hamiltonian is quadratic and of this form.
So you just verified that, but like, how to prove it? Like, I don't know.
No, that's easy to prove. Just think about it. It's very easy to prove that. So first of all, you can always write your Hamiltonian, as I said. So if there are A daggers or something, you can always do the Bogoliubov transformation and then write everything in terms of these. And then so you can always make your Hamiltonian of this form. Any quadratic Hamiltonian basically can be written in this form. Okay, A dagger P AP up to some Bogoliubov transformations. You can always put it in this form. And then of course, and then it preserves the, then as I said, it is easy to, then we verified that it's true. So suppose now you have higher order terms, right? You have A daggers, so say 2 A daggers and 1 A, right? And if you do that, then you can easily see that A of t will have an A squared term or A daggers. You will have some it will not be of this form. It will also be nonlinear in A's. So then it will, so this linearity hypothesis will be simply violated. So when I'm saying this, that I'm assuming something like this, is already true that I have committed to a specific Hamiltonian. All right. So therefore, let me rub it out. I guess it should be obvious.
So sir, the field will always depend on the type of the Hamiltonian we have.
Sorry, again. The field will depend on the type of Hamiltonian. You mean it will depend on epsilon of p? That's, yeah, it will depend on the type of the Hamiltonian, of course. So we are going to construct it. Okay, so that's the whole point. So I'm going to construct the simplest quantum field theory by using this postulates of locality, causality, and that I have a consistent algebra. So basically the idea is as follows. I should be able to write down a way to understand my algebra, my evolution without looking at the state. As I said, if I have a measurement in a domain in some region, I can make some prediction within the domain of dependence, right? That was the idea. And this is something that, so essentially this is true for a classical theory, right? So if you remember that for a classical theory, this is true. And it is also true for a quantum theory. And that's what I'm going to show. So I don't have to know the state. I only need to know the algebra of observables. But let's see. I mean, let's slowly see that. For the moment, is it clear that this is a hypothesis, and this already means that my Hamiltonian is quadratic? So that's the first postulate, if you wish. And the second postulate is that phi of x transforms as a classical field, or has a transformation behaves like a scalar. So let me say behaves as a Lorentz scalar.